You've seen it everywhere, right? On your water bottle, your food containers, maybe even on your receipts. That little label that says BPA-Free. It's supposed to make us feel safe. But what if I told you that might not be the whole story? Today, we're going to look at the chemical that often steps in to replace BPA, and we're going to ask, is it actually any better? So imagine you're in the store. You're trying to make a healthy choice, so you grab the product with that BPA-free sticker. You feel good about it, but have you ever stopped to think about what they're using instead of BPA? And the really big question is that replacement chemical truly worry-free? Well, let's dig in. So, meet the main character of our story today, Bisphenol S, or BPS for short. Now, BPS is basically a chemical cousin to BPA. Their structures are really similar. And because of that, it's become the #1 replacement in all sorts of things. Canned food linings, plastics, and yeah, that shiny thermal paper that receipts are printed on. This brings us to the real question. Are we just trading one problem for another one that's just slightly different? To get to the bottom of that, we're going to dive into this really fascinating scientific study. And this isn't just a simple case of what happens when you're exposed to something. No, this is a story that actually unfolds across generations. It looks at how a mother's exposure can ripple down and affect her children. Okay, I know this slide looks a little complicated, but the main idea behind it is actually pretty straightforward. Scientists set up an experiment with pregnant mice, and the whole goal was to see if exposing the mothers to BPS would have any lasting effects that were passed down to their babies. The investigation itself was super methodical. So step 1, they gave BPS to the pregnant mice. That means their babies were exposed to it, first through the placenta and then later through their mother's milk. After the baby mice were old enough, they were put on a high-fat diet, which is meant to mimic the kind of high-calorie diets that are pretty common for us humans today. And then finally, it was time to sit back and analyze what happened. And you know what? The analysis started turning up clues almost immediately. The first batch of clues were physical changes, things you could literally see and measure. And the first big thing that jumped out at them was weight. You can see it right here in this chart. The offspring that had been exposed to BPS early in life gained a lot more weight on that high-fat diet than the mice that weren't exposed at all. But it wasn't just about packing on the pounds. The researchers also looked at how well the mice can handle sugar. And what they found was that the BPS-exposed mice were showing signs of reduced glucose tolerance and insulin sensitivity. To put it simply, their bodies were really struggling to manage their blood sugar. And that is a classic red flag for metabolic issues down the road, like type 2 diabetes. So then they zoomed in, way in. Looking under a microscope, the picture got even clearer. In the liver, they saw signs of cellular stress, even cell death. And look at this comparison. On the right, you can see how the fat cells from the BPS mice are huge, just visibly swollen, compared to the normal-sized cells from the control group on the left. Okay, so we've got the what, the mice gained more weight, and their bodies weren't handling sugar properly. But that's just the start of the mystery. The real head-scratcher is why. What was BPS actually doing inside their bodies to cause all of this? To find the answer, the researchers had to follow the trail deeper inside the body. And that trail led them straight to the fat tissues, because as it turns out, not all fat is created equal. The easiest way to think about it is like this. Your body has 2 main kinds of fat tissue. First, you've got white adipose tissue, or WAT. Think of this as your body's pantry. Its job is just to store energy, to store fat for later. Then you have brown adipose tissue, or BAT. This stuff is the exact opposite. It's like your body's furnace. Its whole purpose is to burn fat to generate heat and keep you warm. So when the scientists looked at a whole bunch of different tissues, the heart, the liver, you name it, they found their hotspots. The white fat and the brown fat were by far the 2 tissues showing the most massive metabolic changes. This was where the action was. And what they found inside these 2 types of fat? Well, nobody saw it coming. It was a total metabolic plot twist that explained exactly how BPS was causing so many problems. Okay, so to understand this twist, we need to introduce one last player, something called carnitines. Now, just picture carnitines as a fleet of tiny delivery trucks driving around your body. Their only job is to pick up fatty acids, which is the fuel, and haul them over to the mitochondria. The mitochondria are the little furnaces inside your cells where that fuel gets burned up for energy. And here is where things get really wild. It turns out BPS was creating a bizarre metabolic tug-of-war. In the white fat, remember that's the pantry, BPS caused the number of those carnitine delivery trucks to plummet. This created a massive traffic jam. Fuel couldn't get delivered to the furnaces to be burned, so it just got stored as more and more fat. But at the very same time, in the brown fat, the furnace, the complete opposite happened. The number of delivery trucks skyrocketed, kicking the fat-burning furnace into total overdrive. It's like the body knew something was wrong and was desperately trying to fight back. As the white fat was being forced to store all this extra fuel, the brown fat went into hyperdrive to try and burn it all off. It's literally like slamming on the gas and the brakes at the exact same time. And this internal battle, this intense competition between storing fat and burning it, that's what created the deep metabolic imbalance that led to all the health problems. So what's the big picture here? This isn't just about a chemical that makes you gain weight. It's much deeper than that. It's about a chemical that creates a fundamental, high-stakes conflict right inside your body's energy management system. In this diagram, this holds the whole story together beautifully. You can see how the BPS exposure throws a wrench into the works in the white fat, blocking its ability to process fat properly. As a response, the brown fat freaks out and tries to compensate by revving up its fat-burning engine. And it's that intense competition between the two that ultimately fuels the obesity and insulin resistance. So, let's just quickly recap the main takeaways. We learned that being exposed to BPS around birth can make you more likely to develop obesity and insulin resistance later on, especially if you eat a high-fat diet. It works by messing up how your storage fat, your white fat, burns fuel. Your body tries to fight back by kicking its fat-burning brown fat into high gear. But this internal war is what really causes the unhealthy imbalance. And get this, they even found that some good gut bacteria increased, which suggests the body was trying to fight back on multiple fronts. Pretty incredible. And look, don't just take my word for it. The scientists who did the study said it themselves. They wrote, and I'm quoting here, "The unexpected competition between WAT and BAT may play a significant role in causing the health problems they saw. This wasn't the mechanism anyone expected to find, but it turned out to be the absolute heart of the story." You know, this whole study is just an amazing look at how complex and resilient our bodies are, how hard they fight to keep everything in balance, even when they're hit with these chemical exposures. But it leaves us with a pretty big and maybe unsettling question. In this modern world where we're surrounded by thousands of chemicals, how long can our bodies actually keep up the fight?